So, yeah, like Sebastian mentioned, this Congress should have been organized in previous year, April, when I was working for Döhler doing this presentation. Immediately, in the meantime, I moved over to Friesland Campina. This presentation, this knowledge has been gained at my time at Döhler, and also from that point of view, I would like to give them the credits. So, the presentation, what is it about? It's first about discovering, the topic has already been addressed, what is relevant microbiology. And when you know what is relevant, you can look into the specifics of the microbiology, and in this case also the heat resistance of them. When that is known, calculation of pasteurization units and F values, in going towards how to use those values, those calculations in a production process, and actually allowing you to save energy on a pasteurization or a sterilization process. Be advised, the information processed here in this presentation is regarding the European legislation system, and everything will be in the metric system. Heat treatment is the most common treatment that you have in order to control microbiology. However, what is often the case is that the values used at the production process are historically based. For years on years, a specific time and specific temperature of the installation is chosen. And that's usually based on the highest capacity of the production line, with the which means the shortest holding tube, which means the shortest time that the product is actually at a specific temperature in order to have the microbiological reduction. However, there are several factors that can influence a production line's speed / capacity. It could be viscosity, it could be degradation of a pump losing its efficiency. Maybe it's even a new type of packaging that requires a production line to run slower than it was designed for. Or the cooling temperature has to be increased, which means that the cooling section needs more time to reduce the temperature, which means basically you have a longer holding tube. So are many more reasons that a holding time can be changed over the time. So each organism, either micro or macro, has a specific range of parameters that it would like to be in. You have an ideal range that they can flourish, you have a range that they can survive, and you have a range that they decline. For example, one of the most known examples is, of course, pH for microbiology. However, you also have other conditions, like water activity, the presence or absence of polyphenols or oxygen, carbon dioxide, ethanol. These are all hurdles that a microorganism needs to overcome if it wants to grow. And even for an Olympic hurdle sprinter, place enough hurdles and sometimes she or he will fall down because it's simply too much. In that regard, also you have specific conditions regarding storage and packaging that are of influence if an organism is actually relevant. These conditions together are what basically determines what the decimal reduction time and the thermal resistance of the microorganisms are. All of them are basically under influence of the matrix of which a microorganism is in, as Astrid already explained. If I would define the decimal reduction time, it's where approximately 1 log or 90% of an organism is reduced during your elimination step. Whether it is pasteurization, it's filtration, it does not really matter in that case. Most commonly, it's indeed mentioned that a log 5 reduction is regarding the standard for a pasteurization process and a log 12 for a sterilization process. The heat resistance is the change of temperature to influence the D value by a factor of 10 or 90%. Well, I don't know of all the microorganisms that there are in the world or that are relevant for spoilage, I don't know those values. Fortunately, we do have a database, in this case an example from the LAMGO database. It is an open source, however, it's not updated anymore, so that's a shame. What is the case is that it's really important to look at not just the values, but also at the medium in which it is tested. Some organisms are tested in butter oil, some are in microbiological broths, and those all have influences on the D and the Z values. To determine the specific production process for every organism that you want, it's too much work. So we can simplify it by using reference microorganisms. Microbiological effectiveness of a heat treatment basically comes in three flavors for the juice industry. You have the F values that for sterilization of pH neutral products, and in this case, as a microbiologist, I would say pH neutral is equal or larger than 4.5, even though it's quite acidic. You have your pasteurization values at 80 degrees Celsius and at 60. The last one more for carbonated drinks, beers, etc. If I would define a pasteurization unit, it would be that the heat treatment is equivalent to 1 minute at a specific reference temperature. As the calculations come, you also include the lethality equivalent, which is, like I mentioned, the amount of time at a specific degree. Now here it becomes interesting, as pasteurization units at 80, PU80 can be connected to the D80 value. So if you know your organism, you know your decimal reduction time, with your pasteurization units from your production line, you can make the link and calculate how many logs of reduction you actually have, what you need. And by doing that, there are two very common formulas. These formulas are described in several pieces of literature. However, not often it's understood where they come from. Well, the time is simple. Basically, the flow of your production line in cubic meters per hour, calculate to seconds, and then the volume of your holding tube. That part is easy. Difficult part is that both formulas are actually a mathematical simplification of the formula 10 to the power temperature minus reference temperature divided by the Z value. This formula has been described by Boll in 1924, and it still holds today. If I would have the pasteurization unit 80, then my reference temperature becomes 80 degrees Celsius and my Z value 10 degrees Celsius. Unfortunately, I have not been able to find the specific organism that was used for this reference, but every calculation holds up to the upper formula. For the PU60, I could find that the values are equal to that of Lactobacillus brevis, an organism mentioned today already a few times. And the same formula counts for the calculation of F values. It's the same formula, just with different reference temperature. And now it becomes interesting, because if the PU values and F values are determined regarding your relevant microbiology, your application, your packaging of your product, and the shelf life it's required to, then we can really start on making our production line smart. In a rule of thumb, if I would go for carbonated beverages / beers, the PU60 values are used over here. For fruit juices, still drinks, waters, you basically go for a PU80 of 10 if you want to have an aseptic product. And this is a target pasteurization unit. It's not the lower limit. If you work from fresh fruits with a higher chance of contaminations, for example, strawberries just coming from the field, you can choose to go a little bit higher in your heat treatment, going to 40 minutes. And if you want to control Bacillus, then you need at least a heat treatment equal to 250 minutes at 80 degrees Celsius. and this will only result in approximately a log 2 reduction. That's strong is the resistance. Of course, and I mean that in general, it is important that you just have a homogeneous development and homogeneous distribution of the temperature in the product. Meaning that if you have an indirect bottle heat treatment through a tunnel heat exchanger, you really need to make sure that the temperature inside the bottle is homogeneous at your set point and not stop too early. However, the same thing counts for cooling it down. Now, the Shigelbacillus can better be controlled by proper cooling down of your product than just by heat treatment alone. So, how do we make our production line smart? Well, if I would have a tubular heat exchanger, like this example, then my holding tube has a specific length and a specific diameter. Well, in this example, it will be a diameter internally of 75 millimeters and a length of 25 meters, which can be divided, for example, by 5 times 5 meter tube. And then you can also include the connectors. This means that at approximately 8,000 liters, I have a holding time of almost 50 seconds, and at 12,000 liters, I have a holding time of 33 seconds. What you see here, if I would put my under limit of the heat treatment at 10 pasteurization units, then usually if I would go for the maximum capacity of 12 cubic meters per hour, it will be put on 93 degrees Celsius that your heat treatment will be performed. The lower limit that the line should go out of production back into circulation, I would put that at, say, 90 degrees Celsius, or basically 5 pasteurization units. And if I would slow down my production line, I could actually go down, for example, to 91 degrees Celsius. And this is an interesting thought, because you have two possibilities over here. You can say, like, okay, I extend my holding tube, extending the time that the product stays at the temperature. And that's the most of the quality parameters or quality degradation is happening at the heating up section, is not the holding section. So you can extend the holding tube. You can also check out, like, hey, if my production line is not running at maximum capacity, can I program my production line such a way that I make my temperature of the heat treatment dynamic? And here it becomes interesting to save energy. Because if your production line is running not at full capacity, but at 8,000 liters per hour, I can basically save up approximately 2 degrees Celsius that I don't need to heat up my product. In a bit, I'll show you what kind of influence that can have. Sterilization processes of equipment is the same thing. If I want to have a 20 F value of 20, meaning 20 minutes at 121.1 degrees Celsius as a reference, with an absolute minimum of 15 minutes, then if I would have, say, I want to have the process done in 10 minutes, then I need to heat up the tank or the equipment to 125 degrees Celsius. If I can take longer, for example, half an hour, then it would be sufficient to do it just at 121. However, what often happens in practice is that the temperature of a sterilization process of your equipment is not constant. It increases, because you generally have an overshoot of your process parameter. It's not uncommon for a sterilization process to be set on like 20 minutes for 122 degrees Celsius. Well, the equipment actually becomes, say, 125 because of the steam pressure that you use, etc., etc. And with that overshoot, you do have an increased elimination of your microorganisms. Which means if the production line is programmed to count the amount of F values the sterilization process is undergoing, it could have been that after approximately 67 to 70% of the sterilization time, you already have reached the amount of F values that you want to have, and basically the production line could have started to cool down at this point already. meaning you're basically steaming, say, 10 minutes extra, using energy 10 minutes extra, well, you don't have to for your microbiological safety. All wasted energy. The same calculations can also count for the sterilization of products which are pH neutral. Of course, here you have the legal limit of 12 decimal reduction of Clostridium botulinum, which means that 2.4 minutes at 121.1 is the legal requirement. Well, to have a safety margin, it's common to set at 5 F values, and when the target of your production process is 9 F values, you're quite normal working. That means that if I have a holding time of 30 seconds for the 9 F values, I would need to go to around 34 degrees Celsius. And if I would reduce that to approximately 60 seconds, or 3,000 liters per hour in this example, then with 131 degrees Celsius it would be sufficient. Now, what you also have in terms of spoilage organisms in this type of field is Geobacillus steatotrophus, which has a 12 log reduction of 42 minutes at 121. Which means that in these examples, the production setting should be around 138 to 141 degrees Celsius in order to obtain that log reduction. Well, ladies and gentlemen, trust me when I say the chances of making caramel are quite significant in this case. Therefore, and also as this is an organism that really needs a high temperature to develop from spores, it would be better to control it via storage conditions instead of just a single heat treatment. Well, I'm talking about energy reductions, and with the common energy situation in Europe and globally, it's quite an important topic, I would say. I'm going to give you 2 calculation examples. One of them is for a concentrate, one of them is for an RTD. And what the heat treatment will be, you start at 4 degrees Celsius, heat up to 92, and then cool down to 4 degrees Celsius. Maximum flow 13.5 cubic meters per hour. The assumption is 1 Brix equals 1% of carbohydrate, 10,000 kilo batch, and the regeneration of the original process is at 40 degrees Celsius. I don't have to give you the formula itself, I made it for you. The interesting part is that if I would reduce my production flow from 13.5 to 8 cubic meters per hour, I can reduce the temperature by 2.9 degrees Celsius. And then I'm staring at exactly 10 pasteurization units. This number is doubled. Why is this number doubled? Every degree you don't have to heat up, you don't have to cool down. And your regeneration part of the whole of the heat exchanger also has more time to actively work. So roughly it is indeed ×2 the amount of energy that you can save, which leads to a 85 megajoules of saving potential in this calculation example. For an RTD, the numbers are a little bit different. What are they different about is that the flow is higher because it's less, the solution is less viscous, meaning you still can have a significant high production speed. However, as water is more than double the amount of energy requirement per degree Celsius to heat up, you even have, with a 1.5 degrees Celsius reduction, a higher energy saving. In this case, approximately 111 megajoules that you could save if your production speed is slowed down compared to the design of the equipment. All in all, making your pasteurization temperature dependent on the flow could save, in these 2 examples, approximately 5.5% of energy, which is a significant reduction. That is the power that you can use when you make your production line smarter. So to understand these calculations, you can also have a more better comparison of heat treatments. I know the mentioning of a quality department, like, okay, yeah, but an auditor wants to have a fixed temperature. No, an auditor from either ISO, from FSSC, from another company, you need to understand what microbiological reduction actually is. And a fixed temperature and a fixed time is fine, but I have not seen an auditor that actually makes the calculations for the F values and the PU values to check if everything is okay. If you make those calculations for them and have a clear document explaining what you're doing, they will accept it. Because when you compare it to standardized temperatures at 80 degrees Celsius, at 121 degrees Celsius, it's much more simple to compare numbers with different organizations. You can have a reduction of sterilization time of aseptic equipment, and by that an increase of your overall efficiency. Because you can use the line sooner, it needs less time than you have planned for it for your sterilization and your cleaning programs. Also, you reduce energy consumption, which basically means a cost reduction. So you keep the microbiological safety of your product at the same time that you calculate. However, you don't overshoot anymore. And by that, you have a cost reduction concerning only relevant microbiology, and tuning the temperature to the flow of the production line, and use the temperature axis during sterilization processes instead of just having a fixed parameter. With the current software and the computing power that most of the production lines are being run, these calculations can be easily programmed by a skilled software programmer. And actually, why not use it? Use the knowledge from 1924 in current days. So for this presentation, I've used several literature sources, all cited over here. And I would like to thank you for your attention on the late afternoon.